Okay, this video should hopefully be a lot shorter than the last two videos I made. This one is going to be on the topic of kinetic energy. Kinetic energy is just the energy of motion itself. If an object is moving, it possesses kinetic energy. If it's not moving, it doesn't have kinetic energy. Kinetic energy only involves two variables, mass and velocity. So, as I said before, if you have an object and it has mass, and it's moving, it has kinetic energy. So mass we use kilograms, velocity of course we use meters per second, and we square it, we end up with kinetic energy is equal to half the mass times your velocity squared. So it's a pretty quick, easy equation to work with. So I won't spend too much time on this page. As a reminder from the last lesson about work, work is a transfer of energy. So any object that has an applied force acting on it that causes its velocity to change will experience a change in energy, and specifically, it's going to experience a change in kinetic energy. This equation, W is equal to delta E, work is equal to your change in energy. For now, we're just going to focus on the kinetic energy aspect of it. Soon we will get to potential energy, but for now you can just use kinetic energy. And you have seen what that equation looks like in the last presentation. Your change in energy is the difference between your final kinetic energy minus your initial kinetic energy, which gives you this equation. And I got to this equation a slightly different way using the work is equal to your force times your displacement. But I got to the exact same equation for a change in your kinetic energy on the last video. Just a word of caution, when you guys are doing your practice problems, if you're given two velocities, do not do what you see down below. Don't find the difference in your two velocities, then square it. Actually work this equation through properly, or just find your final energy minus your initial energy. So either way, it shouldn't be too difficult for you guys. So I cannot go on forever about that theory. It's pretty straightforward. So let's just try a couple of problems. So basically any question that you've seen in the past in the first two units, so kinematics, statics, and dynamics, I can now incorporate work and energy problems. So for the first example problem, we have a skateboarder with a mass of about 65 kilograms, and he's going down an inclined plane, and he speeds up from 1.75 meters per second to 4.2 meters per second. So he's speeding up as he goes down an inclined plane. What is the increase in his kinetic energy? Could have also asked how much work has the skateboarder done. So if you visualize a little skateboarder dude, that's my best drawing I can come up with. I was too lazy to Google a picture. So there's a skateboarder, he's going down the incline. If this was last unit, I'd maybe make you guys calculate what his weight is acting down the inclined plane. But with the information that you see in this question, this is not necessary. We can just stick with our work is equal to our change in kinetic energy, because I know how fast the skateboarder was going at the beginning, and I know how fast he is going at the end. So I'll just find the difference between my two energies. So my final kinetic energy minus my initial kinetic energy. So 1/2 mass velocity final squared minus 1/2 mass multiplied by your initial velocity squared. Typically, I just factor out the half and the mass. Just makes my mathematics a bit easier. Plug in what you know. It's just a matter of working the equations through. You guys shouldn't have too much difficulty with this. You should have approximately 474 joules if you work that through your calculator. Just make sure you get your order of operations down as you multiply this through. You could have also in step 2 here, you could have also just plugged the numbers in at this point here if you're more comfortable with that, and you probably would have got a final energy of roughly 574 joules and minus an initial energy of, I think it was like 99.5. I just rounded it to 100. So it's not a perfect 474. It's just a rounded figure. But in both cases, you should get the exact same results. So it's not too hard to work with. The second example that I'll do with you, and only example I'll do with you, is an object that is falling down. So this is found in your workbook. I forget what page it's on, but it's question number 17 in the kinetic energy section, probably around page 49 or 50. Little Priscilla drops her 500-gram Spider-Man action figure from the top of a 10-meter high building. If the toy hits the ground at 7 meters per second, calculate the average air drag force acting on the toy as it falls. So this is not a free fall problem. There is air drag. We're going to assume that air drag is constant. I know that's not actually the case, but you can deal with that another time when you guys start integrating your calculus into your physics. But for now, we're just going to assume it's a constant air drag force, even though the question did ask for the average, but we'll just pretend it's the constant force. And at no point in this question does it say anything about kinetic energy or work specifically. It's giving you parameters that you would have seen in Unit 1 and, well, actually Unit 2 because of forces, but it involves kinematics and dynamics. So you could solve this just using what you knew previously, but I encourage you to try to use the work energy theorem, where work is equal to your change in energy, and we're specifically just talking about kinetic energy. I'll involve gravitational potential energy in future classes. So knowing that work is your net force multiplied by the displacement, and your change in kinetic energy is just going to be half your mass times your final velocity square minus your initial velocity square. We are going to probably need to draw a Freebody diagram in order to do this, because for our net force, you have to consider the two forces that are acting. We know one of them was given to us in the question. It says average air drag force. And the other one that must be in this question is going to be the toy's weight. So the weight of the Spider-Man action figure is causing it to fall down towards the ground. So if I draw my free body diagram, I'm going to make down as the positive direction because that's the direction it tends to fall. So the weight vector arrow is drawn down. The drag force is going to have to go in the exact opposite direction. Think of air drag like friction without having to touch the ground. So those are the two forces involved. Put that into your equation. And again, as they are vectors, I'm adding my vectors always. Recognize that Spider-Man was dropped, so therefore its initial velocity is 0. So technically our change in energy is just going to go and be our final kinetic energy, because our initial kinetic energy was 0 because it was initially dropped. Other things that you note, if we take the vector notation out of my left side of the equation, so my work side of the equation, so assuming that down is positive, I'll leave my weight as positive, mass times Earth's gravitational field, both positive because it's going down. My drag is going the exact opposite direction, so I'll just make that negative rather than having to multiply it by cos of 180 degrees. I'll just call that negative and avoid having to bring trig into this equation. Because drag is similar to friction, it's just going to oppose the direction of motion for the most part. We won't get into winds and tornadoes and eddies. That'll be a little bit different. But drag is going directly in the opposite direction. So if you substitute in all your parameters, so your mass, your weight, your displacement, the 10 meters that Spider-Man dropped, I didn't follow sig figs as I typed this out. And of course, your 500 grams after the fact, your 7 meters per second when he hit the ground, so that'll have to be squared. So just plugging in everything that we know so far, and this is what it looks like. Again, I took the vector notation out of my drag, and therefore it's negative. I'll just leave that as red to kind of really highlight it. So if you simplify your math a little bit, Spider-Man has a weight of roughly 4.9 newtons. It's going to travel 10 meters down. When it hits the ground, it'll have a final kinetic energy of 12.25 joules. So let's clean this up a little bit more. We don't need that 10 meters there. So let's divide that out on both sides. So on the right-hand side here, a joule divided by a meter. Let's convert that joule to a Newton meter, because that is what one version of writing down a joule is. So it's either a kilogram meter square per second square, or you can simplify it to a Newton times a meter. So that way our meters actually cancel out. On the left-hand side, the 10 meters also cancels out. So we just transferred that displacement to the right. And I'll just rewrite it. So we end up with roughly 4.9 newtons minus my air drag force should be equal to about 1.2 newtons. I'm keeping the extra digits. So if I manipulate my equation, if I bring this 1.2 newtons to the left-hand side and bring this air drag force to the right-hand side, looks like that. It's just a matter of finishing it off, and you can find the magnitude for your air drag force to be roughly 3.7 newtons in strength. If I didn't introduce my direction and just left my drag as a vector, everything else would have stayed the same. I would have just left the vector notation above this FD, and it would have been positive, and I would have worked down to a negative result in the end as a vector. So this is just the magnitude. I've already taken account for its direction, so this is just the overall strength. So in this question, I never once asked for energy, and I was able to use energy to solve for my drag force. So you're going to find in your work problems and your kinetic energy problems that sometimes it'll never ask you to calculate kinetic energy or even work at all. You just might have to use your equations and manipulate it through to maybe find some other parameters like final velocity, initial velocity, displacement, or mass. So it's just another way of solving for different parameters. I'm going to stop this presentation here. It does spill into other types of questions. You can get into uniform circular motion with kinetic energy, but if you do any of those uniform circular motion problems involving kinetic energy and work, always remember that there is no work done by your centripetal force. And that's because when something is going around in a circle, your centripetal force will make a perpendicular angle with your velocity. So try to remember that if you try to do some uniform circular motion problems with kinetic energy and work.